Today we'll be looking at the integrity protection problem in 5G fronthaul networks. Today's 5G RAN are designed with two key principles. First, disaggregation. Traditionally, a base station was a monolithic block known as BBU talking to a dumb radio head called RU. In modern 5G, the BBU is split into two components, a distributed unit or DU and a centralized unit or CU. In modern 5G, these CU, DU, and RU components, they are connected by open interfaces and communicated through Ethernet-based protocol. The second principle is virtualization, which means now the 5G function can run commodity off-the-shelf servers instead of closed proprietary hardware. With these principles, modern 5G RANs are usually deployed like this. A single CU can serve multiple edge sites, each hosting several DUs, and each DU can in turn support one or more RUs. And each RU can provide cellular service to numerous user devices, such as mobile phone or IoT devices. In this talk, we focus on the interface between the DU and the RU, which is called the fronthaul network. To make it simpler, let's consider a scenario where we have a single CU, DU, RU, and a connected UE. The fronthaul network is responsible for transmitting data between the DU and RU. It operates over Ethernet-based ECPRI protocol. I want to highlight two types of data. First, the user data that is generated from the higher layer. And second, the broadcast messages that's generated by the DU, which includes the cell-related information and the reference signal for channel quality estimation of UEs. The DU takes this data through the signal processing, convert them into IQ samples, encapsulate them into Ethernet packets, and get sent over RU for the over-the-air transmission. One problem of the fronthaul is incomplete integrity protection. Specifically, user data is encrypted from the higher layer using a protocol called PDCP. But the broadcast message generated by the DU is not encrypted. And this is intentional by design because these broadcast messages needs to be interpreted before the UE complete the attachment and set up any security mechanism. So the real issue comes because the fronthaul network does not provide any integrity protection. This will lead to man-in-the-middle adversary who can inject or modify the fronthaul packets. Today, the Oran Island Security Working Group, which is a group responsible for making security specifications, view integrity protection in the 5G fronthaul as optional. One of the reasons they do this is because they have to enable 802.1x for all the components for the ORAN components, which a mechanism to authenticate the devices and enforce access control. This is assumed to be sufficient to prevent man-in-the-middle attacks over the fronthaul. However, what we show in our talk is that man-in-the-middle attacks can be practical and feasible in this setup because of the 5G edge site deployment mode, where you can find the edge site in the public space like the sidewalk, the rooftops, or the basements. Essentially not the traditional data center setting with strong security guarantee that you might be thinking of. So the adversary can easily access this edge site to plug in a rogue device to work around to bypass the 802.1x. This has been shown by the prior work. Another reason is that adversaries assume to require costly sophistication to bypass the higher layer integrity protection mechanism like PDCP. In contrast, what we observe is that this isn't exactly true. as I mentioned earlier, the PDCP protection is actually incomplete because it only protects the messages generated from the higher layer and does not provide any protection to the messages from the lower layer or the pre-attachment messages before the UE set up the key for the PDCP. Finally, the third reason is that they believe the potential attack, even if they occur, will have low severity and will only impact a single DU or single RU. In contrast, we observe that these attacks can be highly severe, impacting large geographical regions because of the special deployment mode of the 5G runs. Even if the attack originates from a single RU, it can affect the CU to impact all the connected edge sites. We'll see this later. Let's see how an attacker can achieve the attack for high impact. The first class of man-in-the-middle attacks we proposed in this work is called Fronthaul attack. It is based on the observation that in normal cases, the DU and CU exchange certain control messages infrequently under certain events, like handover. The right figure, the figure shows the process for cell handover. You don't need to read the message detail. You just need to know that to complete the handover, the DU and the CU need to exchange a sequence of messages. The idea of this attack is to flood the CU with a large amount of such messages. This can lead to degraded cell performance or even denial of service because of the busy CU. And more interestingly, because of the 5G O-RAN deployment mode, where a single CU can serve a multiple edge site, our attack can impact a large geographical regions. Even the cells not directly used by the attacker to launch the attack can still be affected. Now let's consider a concrete example where the attacker maliciously exploiting the handover mechanism to cause signaling storm at CU. Suppose normally there are two cells served by a DU. Let's see cell 1 for the left and cell 2 for the right. The man-in-the-middle attacker can see the Fronthaul traffic sent to both cells, so she can multiplex the signal and create overlapping cells. Now, UEs from both sides can perceive two cells simultaneously, and the attacker can tune the signal quality of the cells by changing the weight parameters as shown as alpha and beta here. Suppose at T1, cell 2 signal quality is better for the left, and cell 1's quality is better for the right. So these two cells will be different from the cell the UEs have attached to at time 0 in the normal case. So this will trigger the handover process of all the UEs from the original cell to the new cell with better signal quality. This will generate a large amount of concurrent handover requests to the CU, causing signaling storm at the CU side. After that, at time 2, the attacker can swap the value of the weight parameter to trigger another round of handover. We have validated our attack using a commercial-grade 5G O-RAN testbed. Our testbed has one CU server connected to 2 DU servers. All components are O-RAN standard compliant. To set up a multi-cell environment, we connect 4 RUs, namely 4 cells, through a switch and attach 8 phone and Raspberry Pi UEs to them. They are placed across 2 floors in a building. And the attacker run a DBDK-based mailbox between the DU and the switch to launch the man-in-the-middle attacks. The figure on the right shows the result of the handover signaling storm. With only 4 UEs, we were able to generate around 3,000 messages to the CU. And note that a cell could typically have at least 40 UEs attached at any time, which means they could generate around 1.8 million messages per hour. This can lead to severe congestion at the CU. In addition to handover, we can also launch a Fronthaul attack using cell reselection. At high level, the attacker swapped the traffic steer direction, sending cell 1's traffic to cell 2, sending cell 2's traffic to cell 1. This will trigger a process called cell reselection for all UEs, generating concurrent requests to the CU and cause signaling storm. The other class of attacks we propose in this work is called front strike. The front strike attacker manipulates the Fronthaul traffic on the fly, causing degraded cell performance or even denial of service. We have 3 example attacks. Please read our paper for more details. I want to highlight that our attacks are different from the traditional radio attacks. We don't need the presence of a radio transmitter, and our attacks can affect many cells simultaneously. Now let's look at the potential countermeasures. The fundamental solution is to provide integrity protection for the Fronthaul network. For instance, enforcing microsecond for all Fronthaul traffic. The packet sender with microsecond enabled will compute the integrity check value, or ICV, based on the packet content using AES. And the packet receiver will verify the values and ignore the invalid packets. However, making microsecond as a standard for ORAN will take some time because we need to update the software and the hardware in the ecosystem. So at the same time, we can also consider some intermediate solutions through real-time anomaly detection. One way is to leverage the Fronthaul traffic characteristics. The Fronthaul traffic usually has a very well-defined timing pattern like inter-packet delays. And any deviation in this pattern can be used as an indicator of abnormal behaviors. In addition, we can correlate. We can also leverage a higher layer KPIs. For example, by monitoring the number of signaling messages sent to CU, we can detect the CU signaling storm attacks. These methods are effective in detecting the attacks and can be deployed immediately in today's ORAN ecosystem. In summary, we studied man-in-the-middle attacks over more than 5G ORAN Fronthaul in this work. We have found that the current ORAN standard underestimates the criticality of the man-in-the-middle attacks from 3 aspects. We validate our observations by designing 2 types of man-in-the-middle attacks and evaluate them using a commercial-grade 5G ORAN testbed. Based on our findings, we suggest reassessing the criticality of man-in-the-middle attacks in 5G ORAN Fronthaul and enforcing mandatory integrity protection as fundamental countermeasures. With that, I will conclude my talk, and I'm happy to take any questions you may have. Thank you for your attention.